In class, especially good luck to Jay in his basketball endeavors. We will start off by having a few review questions. So the first one was differences between classical mechanics and quantum mechanics. And I would say if we kind of go back into the very beginning when we were talking about Huygens and Sir Isaac Newton, they said that light was a wave or a particle, meaning, first off, there was certainly some question on that, right? But they were firmly of the belief that it was one or the other. So I'm going to stress that word or. But quantum mechanics says that light is both a wave and a particle, meaning that we have that duality that's sometimes referred to, and that was accredited to, let's see, de Broglie. He's the one that said, if light can behave like both a wave and a particle, meaning it can be quantized, then why can't an electron behave like a light or like a particle and light? And that's what led him to the idea that the orbitals were quantized because only specific wavelengths of light could fit into each orbital. Probably the second one, what we kind of said, is classical things were generally considered continuous, meaning all values allowed. Certainly for our description of light, that was true, but we know that light, or at least the energy involved with it, is quantized. And that's due to Mr. Planck, who got an entire constant named after him, which is awesome. And then the other thing that we kind of can mention is that, and this is where, you know, I'm making a broad statement that's not totally correct in its statement, but classical mechanics is usually describing things on a macroscopic scale. So that means things like, you know, Heisenberg's uncertainty is not noticeable. Quantum mechanics is generally on a micro, and really we should say nano scale, but you know, that's kind of beyond that, or even lower, as far as meaning that it only applies to things that are tending to be very small, like atoms and electrons. And so here we have to worry about Heisenberg. Heisenberg is a problem, I guess, other than the fact that he's a drug dealer. Did he die, by the way, in the movie? Or in the end of the show? I don't know. Okay. I was just curious if they were going to kill him off or not. Did you have a question, Haley? Is a problem, meaning we have to worry about the Heisenberg uncertainty principle, meaning we can't know both the location and the position of an electron around an atom. And so classical mechanics is always what I kind of think of as, it generally makes sense to us because we're used to seeing all of those phenomenon on the size scale that we deal with. You know, physics and motion and all of those things are pretty reasonable to observe. We can't observe most of the stuff in quantum mechanics, at least not visually, not with our eyeballs. And so it's harder to get a grasp around it, or it's harder to get a handle on it when we don't have it sort of visible. So I know the other question was on scientists, but that's a huge topic that could certainly take up at least 15, 20 minutes or an hour, you know, depending upon how in-depth we want to go. I'm going to say that that's probably best stuck in either a study session, or if people want to stick around after class, we can cover that. But we do have to actually kind of move on to some Chapter 11 material at some point.
Well, it's just mostly because we have to turn it in. I'm sure it's what we're talking about.
Right. So, okay, name a specific question on scientists. Don't just say scientists in general. Ask a very specific question.
Couldn't find the experiments. Is there, like,
Well, not all of them had an experiment. The idea was that it's an experiment or their major finding, right? Their major contribution. Yeah, drawing the models would be a good way to answer that question. Really, the question, if I remember right, isn't it stuck on there as an extra credit question in there anyway or something? Or not? Or is it an actual question? Oh, I think I just threw it.
Go over it, please.
Do you want me to go over the entire homework 10B?
No, just name the experiments that are associated with names. I'm okay with the contributions. I couldn't find angstrom at all, anywhere.
Okay, so these are the type of questions I really would love if people brought to study hall and lab. Meaning, I've only got 50 minutes to lecture on new material, so I can't cover, 15 names. Okay, Huygens was the wave theory of light. Newton was the corpuscular theory of light. Angstrom was the one we skipped because I said I couldn't remember his name. And he's the guy that came up with line spectra, or first measured them. So obviously he won't show up on a test if I accidentally skipped him, right, in lecture. Planck is black body, Einstein is photoelectric, Rutherford has his model of the atom, Bohr has his model of the atom, de Broglie has his model of the atom, Heisenberg uncertainty principle, Schrodinger's is the wave equations for where an electron is, and Pauli was the Pauli exclusion principle. And maybe I should skip the experiment column and simply say, what is their major contribution? Maybe that's a little confusing, because not everyone has an experiment associated with their
So if I
art.
left experiments blank, some of them is okay.
That would be fine. For instance, if you left Pauli's, he didn't really have an experiment. He made the observation based on, well, an experiment we certainly didn't cover. Heck, I don't even know what experiment or where he came up with it from. So yeah, for experiment or major contribution, the idea was that it's kind of maybe some of them don't have an experiment, but everyone certainly has a major contribution. I would also say that the question was thrown on there to fill up space and as review, and that a lot of times people weren't even capable of telling me a list of the scientists when they were studying. And to me, the first thing you should be able to do is if you had a blank piece of paper, you should be able to at least write down 90% of them, 100% of those scientists. I mean, I'm not saying as a starter to, be able to put down what their major contribution experiment is. That's the next step. But for me, studying is always about breaking it into steps. First thing is just to know the scientists' names. That gives you a framework to build on. Then the next thing is to maybe pick an experiment or major contribution. And then the next thing after that would be to, try to go for a deeper understanding of that experiment and stuff. I should also point out that on ChemHaven, so slow, Mr. Computer. We did add a couple new things this semester that you might want to try. Boy, whole thing is slow. Unable to connect to the internet. What the hell? Well, it says the little... Well, wireless isn't connected. Well, the two things I wanted to point out is there is practice for writing electron shell configurations and doing the up and down arrows. I don't think you can input necessarily at all into the computer, but certainly you can push the button and compare what you drew and what the computer draws. And then the other ones up there is there's a couple extra study guides, one of them of which lists every scientist and their major experiment that goes with them, or at least most of them. So that's on the website too. So always go there, kind of check out what's there for each chapter. Quite often I have some extra little hidden nuggets of gold, and I'm guessing we're not going to get internet. That's okay. Maybe we'll try it at the end. Was there some more questions? No, I mean seriously, if people have questions, I don't really care if we do chapter 11 or not. I have to just not care so much that we push forward as much. Was there a specific scientist someone wanted a question on, or?
Outer shell is the very last one, right?
It's the one with the highest quantum number, and we only count the S and P electrons in it because we keep life simple. So if we say outer electron shell configuration, what we mean, for instance, is sodium is normally 1s2, 2s2, 2p6, 3s1. That's the last shell.
Okay, so do it with 3s1 or just s1? Like
Three, well,
what is
the part they have in...
for like alkaline metals? So they all have s1.
Right, so the part that's in common is the S1, or that they have one outer electron valence shell. Now, it's nice to say that it's in the s orbital just because that's more detailed than just saying it has one valence electron. So yeah, lithium, for instance, is just 1s2, 2s1, and so the part that's the same is the S1. And the idea is that if they have the same electron shell configuration, that's a good abbreviation. I don't know if that one even is close to making sense, but we'll put it down. Electron shell configuration, then they have similar physical and chemical properties. And the idea is we already knew that things in columns have the same physical or similar chemical and physical properties. We know that they tend to form the same charges, that they form similar compounds. We knew that, but we didn't know why, other than we just simply said that's the way it works out. Well, the reason why is because they have the same outer electron shell configuration. So lithium and sodium behave much the same because they both have one valence electron. They both have one electron that they either want to get rid of. They both have one electron that can form a bond with something. And so they behave pretty much the same.
Valencing is the highest level.
Right. So,
Valence.
like for instance, if we looked at fluorine, it's 1s2, 2s2, 2p5. We'd collect both of those shells and say it has 7 valence electrons. Any more questions on the homework that's due today? Or in the homework that was due yesterday, for that matter? Or the homework that you got back graded and have questions on? It seems like most people are getting it eventually, or at least being able to do it, which is half the battle. I have to be honest, really understanding what electron spin means to me, I don't really know. It doesn't make any sense to me other than there is some property about electrons that simply has two values. It's either plus a half or minus a half, which basically means that when we draw things like this, we should realize that half the p orbital is one color, so that would be where the m sub s half electron is, and that's where the m sub s. Wow, we haven't crashed the PowerPoint in a long time. This is just going to be fun. So let's go uncrash it, which means kill it. Oh wow, maybe we killed more of the computer. Don't send. Takes too long. For the record, I will always, of course, answer your questions. However, there are good times and bad times to ask questions. Good times to ask questions are not, in the middle of a lecture. Although, I mean, certainly like if it's on the actual lecture material. And, the best time to ask questions is before and after lab and during office hours. And if you can't make those, then set up a time with me. But kind of lecture time is the only time I am guaranteed to have all 9 or 10 of my students here, and so we have to try to focus that with mostly, focusing on lecture. So let's take a look at chapter 11. It's going to be broken into two parts. The first part is going to be periodic trends, and the second part is something called, or I break it apart into Lewis structures. Really, Lewis structures is the funnest part of chemistry. How many of you can count to 8? Really, the only student that I have had that hasn't been able to figure out Lewis structures, his biggest problem was he only had 7 fingers, so he couldn't count to 8. Otherwise, everyone else is managed. I finally told him, it's okay to take off a shoe in class and count on your foot. It's perfectly legit when you only have 7 fingers. So I think everyone will be able to get Lewis structures. And then also for Lewis structures, both labs next week. Yes, lab next week is also practicing making Lewis structures. So you'll have so much practice drawing and making and building Lewis structures that by the time the test comes around, usually it's pretty good. You remind me of the time I said something about having 2 left feet, and this girl in the back of the room gets this look on her face, and she's like, "You have 2 left feet?" And it's like, yeah, buying shoes is tough. Let me tell you, you have to buy 2 pairs of shoes every single time, and then you have to throw 2 of them away, or try to find another person that has 2 right feet. It's tough. Suffice it to say, she struggled in chemistry. Yes. It's not a bad thing to be trusting in things like that. Okay, so let's take a look at periodic trends. And what we mean by trends is we're going to be saying what happens as we go across a row or down a column, basically. And so we can make some broad statements about, where an element is on the periodic table, telling us something about its properties. And then realize that 9 times out of 10, if you really want to know the real value, you look it up. So the first trends we're going to look at is atomic size. And so we have 2 trends. And so what we mean by atomic size is if I have an atom, it really is the diameter. Or because it's hard to measure the diameter of an atom, what they really do is they take 2 atoms that are bonded together and they measure the distance between the nuclei. And so that gives us a rough approximation of the size of atoms. Now, when we talk about Lewis structures and bonding, we'll talk a little bit about, the size of those 2, but we don't get into too many details like in Chem 111. So we're really going to just stick into what atoms are big and what atoms are small. So if we go down a column, that's the easy trend. What do you think happens to size down a column? The size of the atom increases. And why is that? What's changing as we go down a column? So I should also point out, right, the weight's also increasing because we're increasing the number of protons. But remember, they're in the nucleus. They have almost no size compared to the electron cloud. And so, yeah, weight's increasing, but we're talking size as physical size, not mass when we're talking about size. So down a column, the size of an atom increases because each row or each step down a column is a new orbital. Or each step down a column, the n quantum number increases. So if we take a look at our periodic table, and I'm not going to sketch the whole thing, but if we kind of look at it like this, this first row is n equals 1, second row is n equals 2, third row is n equals 3. Well, what that's really referring to is, here's the size for n equals 1. N equals 2, the orbitals are further out. And for n equals 3, the orbitals are even further out. So as we go down a row, we also are going out 1 orbital each step down. I'm sorry, as we go down a column, each step down the column is a new electron orbital. So that means the electrons are further out. So what it means is that as we go down that column, they get bigger fairly rapidly, meaning that hydrogen is the smallest element, and if we kind of go down the column, cesium is a very large atom compared to that. So I should also point out that there's 2 levels that I test this sort of material on. The first level is simply, if given the question, down a column, the size of an atom increases, decreases, or stays the same, well, you just have to have memorized the trend, right? The second level is, of course, the part where I always add the word explain, or I even give you the answer and I say, down a column, the size of atoms increases. Why? And so you have to be very careful when you're giving some of those explanations, in that if you simply say the size increases because an atom has more electrons, well, that's partially true, but we're going to find that just adding more electrons doesn't necessarily make an atom bigger. And so the real key reason is that we're going up or out 1 electron orbital each time we go down, or the principal quantum number is increasing. So be careful with your explanations and realize that any explanation you give for one phenomenon can't contradict something else that we know about another phenomenon or another trend that we look at. So what about across a row? This one's difficult. And I got to be honest, to me it's counterintuitive. So across a row, the size of an atom So what's going on as we go across a row? Yeah, so as we go across a row, we gain electrons. What else do we gain, though? What's the difference between, say, shapes are different, so there is some shape differences. One more thing, though, that we gain. We're not just gaining electrons when we go across a row. What else are we gaining? Yeah, protons. And that turns out to be very important. If we take a look at an atom, and notice I'm not answering the question yet, because to me the answer is counterintuitive and it's better to come to it maybe via some thought. If I take a look at an atom, you know, there's an s orbital, there's another s orbital. And remember, there's p orbitals in this too. It's just we're too lazy to draw all the dumbbells, and so we try to stick with the s orbitals. So, you know, here's n equals 1, here's n equals 2, and then there's our nucleus. So if I've got an electron here, what do we know about electrons and the nucleus? Yeah, that's an attraction. And if I have an electron out here, it can also see the nucleus, so that's also an attraction. But what happens if I have two electrons? Right here, between these two electrons, that's a repulsion. So we've got two things going on. We've got electrons being attracted to the nucleus, protons, and we've got electrons that are also repulsing each other. So to describe sort of the war that occurs between those two, we've got a little equation that we can talk about. We have what's called Z effective equals Z actual minus, I call it electron shielding. And so let's define all of those. This is the effective attractive force.
That's Z effective?
Yeah, so Z and the subscript EFF. So that's the effective attractive force. Meaning that the real attractive force also is, well, let's rephrase that. The Z effective is kind of the sum of the attractive force between the protons and electrons minus the repulsive force between the electrons and each other. So Z actual is the real attractive force between, protons and electrons, ignoring any repulsion. So that's basically saying if I just had, say, 7 protons and 7 electrons, how strongly attracted would they be to each other? Or the idea is how strongly attracted is an electron to 7 protons? And then in that electron shielding term, that's what we mean by, this is a measure of the electron-electron repulsion. And it occurs because the inner electrons shield the outer electrons. And don't worry, we'll put some fake numbers in here a little bit, and then we'll also kind of go through it one more time, because this is one of those key concepts that's not obvious necessarily. Jess?
What does that say, effective attractive?
The effective attractive, I apparently stutter even when I write. The effective attractive force, or you can say that it's the overall force. Meaning it's the sum of the attractive part. See, this is attractive. This is repulsive. And since it's Jess's birthday, we'll say this is Jess and this is Jay. I don't know, I'm just being silly. Basically, I always want to talk about protons and electrons and attractive and repulsive forces in terms of supermodels and J, where supermodels represent the attractive forces in nature and J represents the repulsive force in nature. Now, who wins, Jess or J? No, Jess does in this case. So it turns out, now I'm going to pause here for a second and see. Is everyone kind of done writing that down? Because I do have to go to a new slide here in a second. I'll wait for a minute.
Second one is M2.
Second one, what?
Oh, M2. Other one.
Oh, I see. Yeah, N2. There we go. So the idea is that this attraction is less than expected because of the shielding. Meaning the electrons in the inner orbitals mask or screen the electrons in the outer orbitals from seeing the nucleus. That's why it says subtractive. It means that the attractive force is actually less than we'd expected. They're also further away, but you know, it's more, I mean, it's a combination of things. This is a simple formula to try to explain one little thing. Remember, the actual wave equations are much, much more complex than this, and they actually factor in things like distance, and they even factor in the shape of an orbital, meaning an s orbital and a p orbital screen each other differently. So we're taking this at, like, you know, 0th level, meaning we don't want to make it too hard. It's probably hard enough as is. Because the inner electrons shield the outer electrons, or this one's, you know, it's less than expected because of the shielding, meaning the attractive force, it's not held as tightly as you would think. So one of the things is, like, this equation is responsible for, you know how you said that, like, if you're in a 2s and a 2p orbital, you should be at the same energy level? So we had said, you know, that if we looked at a diagram like this would be our 2s, 2p, but that's not really how it is. The 2s is lower in energy, and the 2p is slightly higher, meaning those electrons are a little further away from the nucleus than the s ones. And that's because of this formula and the idea that the s orbitals shield differently than p orbitals. That's what leads to those splittings. But the big take-home message for size, so we're just rewriting the equation real quick, z actual minus the electron shielding, is that as we go across a row, z actual increases. And the reason for that is we add both a proton and an electron. And so every time we add a proton, the electrons are all sort of more attracted to the nucleus. So this means that the size is decreasing based on that part, meaning as we're adding protons, there's more and more of an attractive force, and the size of an atom should shrink, right? Whereas if I look at the electron shielding as we go across a row, then the shielding means stays about the same because we add outer shell electrons. Therefore, the inner shell screening doesn't change much. Now, this would normally argue that, you know, size should increase. So as we add electrons, we'd expect the atom to get bigger, right? But we have to remember, we're not just adding electrons, we're also adding protons. So protons, every proton I add says the nucleus should shrink. Every electron I add says the nucleus should get bigger. Not the nucleus, but the size of the atom should get bigger. So there's a war going on. But the key is that z actual is increasing. The shielding stays about the same going across a row. Therefore, the net effect is an increasing attractive force. Therefore, the size decreases across a row. To me, that's totally counterintuitive, especially when you think that going down a column, they're getting bigger, right, because we're adding more electrons. Well, that's true. But we also have to go back and say, where are we adding those electrons? We're adding them in orbitals that are further and further out. As we're going across a row, when we add those electrons, we're adding them into the exact same orbital, and so that orbital is slowly shrinking as we add more and more and more electrons. And so it turns out that part of the reason why atoms behave the way they do is that complex interaction between the attractive and the repulsive forces. And that leads to a lot of chemistry, and that leads to this fact that the atoms are different sizes means they interact differently. We can make different types of crystal structures with them. As the atoms get bigger, it tends to be easier to gain and lose electrons, so they become a little bit more reactive. There's all sorts of little trends that or chemical features that come from basically just the fact that the size of the atom is changing. So, first level, just memorize whether it increases, decreases, or stays the same. Second level, be able to kind of come up with a good explanation for why this occurs. And just as a heads up, just simply saying as you add more electrons it gets bigger or something weird like that never works, because adding more electrons in this case does not make an atom bigger, does it? Now, adding more electrons down a column, technically the atoms get bigger, but it's not because we're adding more electrons, it's we're adding electrons in bigger orbitals, right? Okay, now all of our trends after that come back to pretty much basically this trend right here. So this is the key one to understand. And if nothing else, understand it on the level of I know it's increasing or decreasing, because that'll get you at least the beginnings of the parts for this. So the next one we want to talk about that's important is ionization energy. And depending upon which class I'm lecturing in, I have to remember to use different symbols. I usually just abbreviate it IE for ionization energy. My other class, though, their book likes to say that that's energy, and then they put the IE as a subscript, saying that that's, you know, there's lots of different types of energies. One of them is ionization. So I'll try to stick with just IE for you guys, but if I screw up, realize that those basically mean the same thing. And this is the energy required to remove an electron from an atom in the gas state. To remove an electron from an atom in the gas state. And the reason we care about that is, think about it, what's the very first step if I'm going to do a chemical reaction between, say, sodium and chlorine to make sodium chloride? What do I have to take from the sodium?
What was the question?
So the idea is, why do we care about ionization energy? Well, the idea is that it's the first step in most reactions. For instance, if I'm going to make sodium chloride, well, one of the first things I have to do is make sodium lose an electron, right? So I have to be able to make sodium plus. That means I have to lose an electron. And so the measure of how much energy it requires to just rip an electron away from an atom is important, because that also determines how reactive it's going to be. If it's easy to rip the electron off, it's going to be pretty reactive, right? It doesn't take much effort. If it takes a lot of effort to take it off, then that element isn't going to be terribly reactive. And so ionization energy, if we kind of write an equation to describe it, it's sodium, oops, not sodium, plus the ionization energy goes to sodium plus an electron. So here we removed the electron, and notice that it requires energy, meaning it's endothermic. And that should kind of make sense, because remember, if I'm taking a look at an electron in an orbital, there's an attraction to that, to the nucleus, or to the protons. Therefore, it takes energy to pull apart. The other way I like to start thinking about this is, it's kind of like magnets, you know. My nucleus has a positive charge, my electron has a negative charge, and it takes energy to pull apart two magnets, doesn't it? Meaning if the magnets are stuck, especially, I don't know, did we get those out? We got the ferrofluid out, and we also got those really strong magnets and saw how hard those are to pull apart. I'm pretty sure that if I had two of the big round ones like this, they're so strong that I don't think I could physically pull them apart. I'd have to like pry them just a little gap and then stick something in between them and stuff. They're kind of dangerous. The person that gave them to me told me that her dad uses them to make, oh gosh, something gas ionization chambers or something to do that vapor deposition, I think, basically. And you need a very strong electric field. And he says, yeah, you have to be careful or you break fingers, because you get them stuck between two of those bigger magnets. Or you pinch your skin or things like that. What is, oh, that's shooting outside.
You can get popcorn too.
Well, I was kind of wondering who was making popcorn personally, but they're just shooting guns off outside. Now I just crave popcorn though. No, not really. It's too early in the morning.
I don't think I've ever had a craving for popcorn. I've eaten it.
Really? I crave popcorn sometimes. Buttery goodness.
Like popcorn?
So let's take a look then. What happens to ionization energy, or as we go down a column, so I guess one, down a column, ionization energy increases, decreases, or stays the same? Yeah, down a column. So ionization energy should decrease. And that's because the electrons are further from the nucleus. Therefore, easier to remove. Meaning, if I take a look at an atom, like for instance, here's lithium, and I guess there's technically, versus say cesium. I'll make those really small. 2, 3, 4. Where is cesium? 4, 5, 6. So there's n equals 6. It's a lot easier to pull apart two magnets that are far apart to begin with, right, than it is to pull apart two magnets that are stuck together. So if we take a look at cesium, its ionization energy is going to be much, much lower than that of lithium. And then as we go across a row, what do we expect? Ionization energy should increase, decrease, or remain the same. Yeah, it should increase. And the reason it increases is because the size of the atom decreases by a small amount. Therefore, if I compare, say, lithium versus fluorine, lithium has a much, much higher ionization energy than fluorine, which kind of makes sense, because who would rather be plus? Lithium plus, or do we ever have fluorine plus? Now, fluorine doesn't really want to give up that electron. It takes a lot of energy to rip an electron off from fluorine. Now, I should also point out in your book that your book has some pretty good figures for this. So, like, for instance, if you want to look at figure 11.3 on page 217, that shows, some actual kind of rough estimates for values and stuff, but it also shows those trends. And you can see that as we go across the row, the ionization energy gets up, and as we go down a column, it goes down. For instance, it's very, 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 very hard to remove an electron from helium, neon, argon, or krypton, both because they've got completed octets, but also because they have or are much smaller than their corresponding, atoms in the same row. So, what this tries to help explain, or at least wants to start helping us understand, is that sodium forms a +1 cation because it's got that lone electron just dangling out there, and it's pretty easy to remove it because, sodium's, and then like cesium, it's a lot easier to make a cesium +1 ion than a sodium +1 ion, simply because cesium has, is so much larger that that electron is held so much looser. Okay, there's one other trend that we want to look at, and that's what happens when we have, say, second and third ionization energies. So for instance, if I take a look at sodium plus, let's see, it takes how much? It takes 496 kilojoules per mole. So notice I'm actually putting a value in for the ionization energy to make a sodium plus ion plus an electron. So this is what would be our first ionization energy, meaning I take away the first electron. The second ionization energy is if I take sodium plus and I want to rip another electron out to make sodium 2 plus a second electron. And the amount of energy for that is 4,565 kilojoules per mole. So notice it takes approximately 10 times as much energy to remove the second electron. And the reason for that, and one of the reasons we want to understand electron shell configurations, is because we can understand what's going on by looking at the electron shell configurations. So for instance, if I look at sodium, it's 1s2, 2s2, 2p6, 3s1. That would be the first electron, right, to be removed. Where does the second electron come from? So I'll hold off for a second. I can still see people madly scrambling to write. Yeah, so there's where that second electron comes from.
Where?
From the 2p orbital, and the first electron is from a 3s orbital. So notice that this electron is in the outer shell, therefore pretty easy to remove. This is from an inner shell, therefore hard to remove. Or the other thing that we note is that it's from a completed octet. And it turns out that those octets, or sometimes we'll call that noble gas configuration, electron configuration, is sort of extra stable. One of the reasons the noble gases don't react, and one of the reasons that there's no known compounds of helium, neon, there might be some for argon and krypton. As you get bigger, you start getting d orbitals. That makes life complicated. But certainly I'm 99.99% sure that no one's made anything with helium and neon except for some weird experiment in someone's basement maybe that we don't care about. And that's because they've got completed octets. They don't want to give up those electrons. They have high ionization energies, and they're pretty satisfied to just be, having those completed octets. There's something, and here's where, again, we're going to invoke a little bit of quantum mechanical weirdness, or maybe not even weirdness, but certainly if you run the mathematical equations for quantum mechanics, it shows that the lowest level energy state for atoms is to have completely filled orbitals. And so that's where the octet rule comes from. It simply says, well, we've got to have 8 electrons to completely fill an orbital. Notice that 8 electrons is just, s2p6. That's a filled orbital. That's exceptionally stable, and that it doesn't want to react. Right. Right. So the reason that sodium +1, or sodium almost always forms a +1, is it's really easy to lose that electron. It only takes about 500 kilojoules. It takes. Well, it doesn't change into a new element, but it looks like it from an electron shell configuration, meaning it's still sodium. But now it's sodium that has a completely filled outer orbitals, 2s2, 2p6, and it doesn't want to gain an electron so much, and it certainly doesn't want to lose any more electrons because they're that much closer to the nucleus. And so it turns out that one of the reasons sodium +1 forms, and that's its most common ion, is because it's just really easy to remove the first electron, 10 times harder to remove the second one. If we take a look at a similar element, except we go one column over, for instance, and say, take a look at beryllium. I don't like orange. So beryllium, to lose the first electron, is, and I'm not going to write the equations out, 900 kilojoules per mole. To lose its second electron, it's 1,757 kilojoules per mole, so not a big jump. And to remove its third electron, it takes 14,845 kilojoules per mole. So what is this? This is like almost approximately a doubling. And to go from 1,800 to 1,400, that's what, approximately 8 times as much maybe. It's not quite 10, but 8 or 9. And if we take a look at beryllium and its electron configuration, it's 1s2, 2s2. And so notice that the first electron is from an outer orbital. It's from an outer orbital. its second electron is also from an outer orbital, but the third electron is from an inner orbital. And technically it's from something that looks like helium, meaning it's 1s2, so it's full and happy for helium. So same thing with, like, for instance, and notice that beryllium is in the column where beryllium plus 2 is the normal ionization. Notice that's the same column as magnesium, and we know magnesium is a plus 2. And so everything in that alkaline earth metal column has got a plus 2 charge because it's got 2 electrons in its outermost shell. They're very easy to lose. Once it loses those, it takes a lot more energy to pluck any more of them out. And so you don't find beryllium plus 3. You don't find magnesium plus 3 in any compounds. And now we can go across the entire periodic table and kind of look at this and say, okay, this is exactly how or why they form these common ions, because they're either trying to get to an octet by losing some electrons, or that those electrons are fairly easy to lose because of the low ionization energies. And we'll look at the other part, which is gaining electrons, here in a second. Oksana.
What is that after inner orbital helium is full?
Yeah, so helium, so we have the octet rule that applies for all the elements except for hydrogen and helium, because hydrogen and heliums are the only elements that lack p orbitals. There is no one p orbital, right? You don't get p orbitals until you get to the second row, just like you don't get d orbitals until you get to the third row or the third quantum number. So helium and hydrogen are the exception to that octet rule in that they're happy with just 2 electrons because that fills their orbital. Okay, we're not going to talk about this in any detail because this one's complicated, but I want to just throw it out there for completeness sake. Electron affinity is how much energy is required to add an electron to an atom. And so that's like, for instance, if I have fluorine plus an electron and I want to make fluorine minus, I actually get energy out of that process. And the reason it's more complicated is because it's really technically defined as the opposite of that. So I'm not going to go into any details. It's not going to be on a test. But basically, think about electron affinity as being the opposite of ionization energy. Ionization energy is how much energy it takes to remove an electron. Electron affinity is kind of the amount of energy that's released when I add an electron to certain elements. But the idea is that we know that, the halogens have high electron affinities because they want an electron. If I take a look at fluorine, it's 1s2, 2s2, 2p5. If I add an electron, then that means that I go to fluorine minus, which is 1s2, 2s2, 2p6. It now has a completely filled orbital, so it makes an octet. Therefore, it loves to gain electrons, which means it has a high electron affinity. And we won't worry too much about, like I said, any details beyond. Think about it as the opposite of ionization energy, because it really is more complicated. For instance, sodium has a 0 or really unmeasurable electron affinity. You can't add an electron to sodium to save your life. And so a lot of the elements end up having 0 values, and depending upon the book you read, sometimes they define them as positive numbers, sometimes they define them as negative numbers, and it gets all complicated and annoying. So one last thing to take a look at, and this one's reasonably easy. So we've got, we'll call that number 3. Do you want me to pause for a second? Well, 4 trends that we're going to talk about, I guess. I don't know. Sometimes I just number things arbitrarily, or I noticed that in my notes I had it numbered. Atomic radius, ionization energy, electron affinity, and the size of atoms, or size of ions is next. So the last thing we want to talk about is the size of ions. Or what we're really comparing is what happens to a cation. So cation versus, say, a neutral atom. Or say, what's the size difference between a sodium plus ion and a sodium, just a normal atom? So what do you think happens when I remove an electron and make a cation to the size? So the question is, what happens to the size of an atom when I take away an electron? Does sodium plus get bigger or smaller than sodium? Because that's sort of our neutral atom. Hmm? Well, why? So you're right, the size decreases. So sodium, yeah, if I remove an electron, then it's from the outer orbital. So you're right. So the idea is that if I take a look and compare sodium plus, that's 1s2, 2s2, 2p6, versus just normal sodium, which is 1s2, 2s2, 2p6, 3s1. I really did, now this only has 2 orbitals. This had, 3 orbitals. So of course it gets smaller. The other reason is fairly easy too, is simply if we remove an electron, but the protons are the same, then we increase the attractive force. So we can kind of look at the electron-proton ratio. Because there's fewer electrons and the same number of protons, it's going to shrink the atom down. This right here. So the idea is that the electron that sodium is losing is that outermost electron. So it's going to lose this electron, right, to make sodium plus. And so the idea is that it's losing that outermost electron, and that's the one furthest away, and so the whole atom shrinks because now it only has 2s orbitals instead of a 3s orbital as its outer shell. Now, I have to be honest, one of the reasons I hit quantum mechanics so hard, and I hit this notation so hard, is when we come to explain this sort of stuff, it makes a lot more sense, I think. And if you don't have that idea of what n quantum number is telling us and that the size of the orbitals and things like that, it makes explanations in Chapter 11 harder. So I hit Chapter 10 harder to make Chapter 11 hopefully a little bit easier, or at least the notation a little bit more interesting or useful. The last one is simply looking at anions. I don't like orange that much. So if I compare, say, for instance, fluorine minus versus fluorine. So, this is neutral. This is the anion. Which one's bigger? What? Yeah, so the anion is larger. And it's not as obvious why in this case, because if you look at fluorine minus, it's 1s2, 2s2, 2p6, versus fluorine neutral, which is 1s2, 2s2, 2p5. So if you notice, the electron that's added is in the same orbital. But that's not, so it's not getting bigger because we're adding a new orbital, right? But the major part here is the fact that we add an electron without adding a proton. Therefore, the attractive force decreases. Or you can talk about the electron, and we'll say it this way, the electron-electron repulsion is increasing before the atom gets bigger. So in this case, the orbitals, or the idea of the orbitals controlling the size of the electron or the atom, isn't as useful simply because we're adding an electron to the same orbital. But if we kind of think and fall back and say, well, in addition to adding an electron to the same orbital, we're really adding an electron and not adding a proton in this case, so the atom is going to get bigger. So it turns out that cations tend to shrink down in size, anions tend to get bigger. And I think we'll just end there. That should hopefully be enough to get you through the first homework, I think. I don't have a copy of it. I was going to use Mr. J. Bradley's copy to make sure I covered everything. What's this? Oh, this is the extra copies.
Yes, I grabbed two.
You took two, Oksana.
It was an accident. Can you explain that again, why it gets bigger? We're not reading another orbital, but I still didn't get why it gets bigger.
Well, because the attractive. Oh, I'm sorry. I actually have an arrow going the wrong way. I said therefore the attractive force increases, but really the attractive force decreases, right? So the idea is that if I've got, for instance, in fluorine, what is fluorine? Number 9. So I've got 9 protons and 9 electrons. But in fluorine minus, I've got 9 protons and 10 electrons. And so each electron sees a little bit less of a proton, and so it's not as attractive as much. And so that causes it to swell, meaning the attractive force is not increasing. It's actually decreasing because we're adding more electrons. Plus, we gain the more electron-electron repulsion, even though they're kind of in the same shell, so it's not a huge amount. And so the atom swells. This should be enough to get you through homework 11A and half of 11B. Now, obviously, I'm not going to have you turn in half a homework, right? So we didn't quite get through as much as I wanted. That's okay. We'll just pick up the second half of 11B on Monday and then transition into Lewis structures, which is fine. So let's say 11A is due Tuesday. And then the other thing that's due Tuesday is Lab X. And then for Tuesday, we're going to do the Lewis structure lab, or at least part of it. And so what we'll do on Monday is we'll take things a little bit out of order, and we might not talk about, well, I think we can actually get there. We might just end up lecturing part of Tuesday to get you started on Lewis structures, and then maybe make part of Wednesday a lab day or something weird like that. Just flip the order we do things in, just so that, because there's a certain amount of explanation you have to have before you try to draw Lewis structures, or it's going to be difficult. Okay, so let's finish up here. Let me stop this. And I need to go start my bread machine.